Close.
You're the host now.
Okay, great. Okay, sorry about that. Somehow I was in this meeting, not as a host, but apparently as a parasite. So now I'm appropriately designated as the host. So I can take this forward. So welcome everyone. We are, apologies again for the late start. We're going to be working today germane to some of the material I presented yesterday to put in place observer processes for a model. Now, to make the best use of time to allow us to focus on this task or this class of tasks, we're going to be building on top of a model that we already built for in a previous lab session. So specifically, I would like to draw your attention to a model which you will find on the appropriate websites. It is called, on the Fields LMS, a minimalist communicable illness neighborhood mobility model. You can go download it from there. Within the side of the U of S site, it's called Minimalist ABM Neighborhood Network Mobility .alp. Now, I'll further share just to allow it to be easily at hand, said model using mechanisms here. I'm sharing it in the chat in case you want to just grab it from the chat. You're welcome to do so, and it should be available for download there as well. Okay, great. Okay, so let's, in short order, open up that model. I'm going to be making up a little bit of time here, so apologies for needing to go quickly. This model, I'll close all others to avoid getting confused. Oops, so I meant to do close all others. Here we go. Okay, so you may recall this model. The essentials of it is we have a overall environment, which has homes, workplaces, community places, and population. Of these, the only one that's really an active agent, an agent that has agency, that's in some sense autonomous and has both characteristics and behavior, is person. Person circulates between environments, home and work, and they have a natural history of infection, which once infected, enters an infective state, effective immediately, where they can expose others after some chance per unit time, that in this case is fixed. They recover, and after a certain period, they can lose immunity. We also have community places, homes, and workplaces. Community places, we could have added in. Conceivably, if all the stars line up, we could do that today. But the basic gist is that people circulate environments, they expose others at their current location. So when someone commutes to work, they move to the workplace, and the exposures, if they are infected, the exposures occur, they expose others to pathogens at that location. By contrast, if they're susceptible, they will be exposed by others who may be infective at that location. Okay, so with that broad recollection in mind, you may recall that when we ran this model, we started with a single person infective, and unless the infected died out, they eventually infected others at their home, and then successively at their work site, and by so doing, those people at their work site will bring the infection home and expose others. And bit by bit, it ends up crossing over between work sites, homes, and it spreads in heinous succession. to occupy a large part of the population. And time goes on, and with a small enough population, it can die out. Otherwise, it can stay present and circulating. In this case, it actually looks like it's still circulating. And we explored before how we could go, and in somewhat brutal fashion, we could drill down to particular community members. We could, not community, places, community. We're looking for the population. Go down to particular community members and see, okay, there's a person at work who's currently recovered, person 0. Person 1 in the population is also at work, not surprisingly, but is susceptible, and time goes on in this sort of way. And eventually, if there are people prevalent, we could find them in the infective state. But this is brutal. It's totally non-scalable. So let's put into place mechanisms for appropriate reporting. Let's put into place, in short, observer processes. Okay. So we will do this as time allows. We'll get further or more tightly scoped. I will seek to share said model periodically via the websites. Okay, so I'm first going to create a second version of this. It's good to keep versions. If you know Git, you can. You're recommended to use Git for appropriate version control here. It's not without some limitations, but generally it's better than simply saving copies of things. But curating copies of things, models with clearly defined version names, and a separate lab notebook that keeps track of what the distinguishing features of each successive version compared to previous versions, and by extension, which runs were conducted with which scenarios of which versions of models is incomparably better than not keeping track of that information at all. Okay, so this is version 2. Okay, we are going to be adding some components to version 2. The first thing we're going to do is the most basic. We are going to go into main. We are going to go down main, and we're going to go to the population. And within the population, we will notice a section called statistics. We're going to press a plus button, and you may need to open this thing that I believe may be called an expando window. You open statistics, and we are going to, so I pressed a plus there, and we are going to create a prevalent case count. So this is going to be a count of people who are currently infective. This is going to be, and so each statistic, we have to delineate what's the aggregation operator for that statistic. Is it a min over some population? Is it a max over this population? Is it a sum of some quantity over a population? Is it a count over the population? And for each of these, there'll be some criteria. A count will just have a condition. We're counting the number that meet some criteria. A sum will sum up some expression, some formula for each person in the population that meets some criteria. An average will average the value of some expression, some formula for people who meet a criteria. The min will take the min of that number, max, with each being delineated by people who match, or limited to those who match the criteria. Okay, so we're going to put in a condition. In order to do this, there's a little light bulb, and it will tell you can refer to the person as something called agent. So we're going to say, we're going to count the number that are in a certain state. These are people. Each agent is the agent in the population. That's a person. And we're going to say in state infected. But as it turns out, we can't just do that. That's a bit too glib, because it says, well, infective, what is infective? Maybe there's people that can be infected and birds that can be infective for a West Nile virus model. Maybe there are cervids, like with that model I showed last time of chronic wasting disease. So we need to say person.infective. It's infectivity with regard to person. Notice this is a capital P. It's actually the person class has a notion of infectivity. So it's referring to this particular state. And it's what, for those for computational background, may find comfort in knowing that it's a static variable. Okay. So having done that, person.infective, we can build. It's a happy camper of a model, and we can run. Now, if we run it, even with just that statistic involved, we secure some advantages. We can go and click on population here, and you'll notice it says the prevalent case count is 6, 5. And right now it's 6, 7, 80, 100, 200, and so on. Okay. So already it reports on these statistics when you click on this interactively. That has a certain virtue to recommend it. We can get information about how many people are infected at any one time. We don't have to guesstimate based on what we see, but we can do a lot better than that. So we will put into place a more usable mechanism for characterizing that, or for visually conveying that. So specifically, we're going to go to the palette. Having opened the palette, we're going to go down to the analysis tab. Having gone to the analysis tab, we're going to drag in a time plot. Okay. Here's the time plot. Dragged in from the palette into main. Okay, this is going to be it's going to be prevalence time, or maybe I'll call it infection status time plot. We could plot, for example, additional things we might plot would be number of susceptibles or the number of recovereds. Okay, so this is going to be a value. We're going to call it prevalent case count. This is a text string. It's just a title. And how are we going to compute said quantity? Well, we just encoded a statistic. That's an operational measure. It's operational. We can call it. We can request that information programmatically. How are we going to do that? Well, we added that to population. It was to population. You may recall that we added this statistic. So in said graph, we will have this value report to population dot prevalent case count. Yes. Now you'll notice it has this open paren, end paren, as everyone here has likely surmised, or many. This is actually calling off to this mechanism. This is, in fact, a function that computes this. It creates a function that we can call, and at any one time we could call off and get that number, and then we can periodically update that graph. And it says every hour. I don't think we need to be quite so granular. We'll say every 1 day. And I can't remember if we put a upper limit on the time. Looks like we go until the cows come home. So I'm going to display up to, let's say, because each is going to be sampled once a day, I'll do 365 days. Okay, 1 year, 1 year of display. So we're going to have this graph, which is going to be updated periodically, and which right now is a single line, which characterizes the prevalent case count. A single trajectory will be shown. We could add more there. Okay, so let's run simulation, and we will graph out this number of people who are infected over time. And here we go. We can see that it's excuse me, this x-axis, I realized. I misspoke. The x-axis is actually in the time unit of the model. The time unit of this model is hours, which means that this is a rather limited. I said 365 days, and I stand or I sit corrected. This should in fact, it is true, it only updates once a day, but this is, well, excuse me, no, it should display 365 samples, which is 365 days, is my understanding. But the axis is indeed in hours. It's shown in hours. Okay, so maybe I'll make that a longer time frame here, just to have it be scrolling less. We may also in this scale, we'll put in a 365 time window. Okay. And I'm just scaling up by a factor of 10. I should have computed 24 times 365 so that I could well, okay. Anyway. Okay, anyway, so we're going to plot this out, and what we will see is a more meaningful experience of graphing the prevalence over time. You see a certain set of circulations as the infection undergoes outbreaks, and then at some point it dies out entirely. It dies out due to stochastics. Okay. So here we have a model that we can now get some semi-useful information out of, like looking at the number of people in the population. I should have noted while running, and forgive me, I'm just going to start running it again. And having started it here, I'll let it run again for a modest amount of time. Here we go. And I'm going to go to this, and I'm going to copy this. You'll notice that there's a little widget up here, a little gadget up here on the upper right, that we can use to good effect. So, for example, if you have Google Sheets up, or if you have Microsoft Office, or you have LibreOffice, you can go and copy this into LibreOffice. And as normal, LibreOffice is troubling me with a bunch of preliminary questions and mumbles. I will go drag this down again, and we will paste this in, and we can get a characterized number of individuals who, after a certain number of hours after the beginning, 24, 48, 72, 96, what the prevalent case count was here. And that could, of course, allow us to create a graph external to this. So I could do insert somewhere in here in LibreOffice. There is a nice little graph widget, and I could go create a little plot. More to the point, I could go save this out as a CSV file, and you could import it to your heart's content into our studio, or R without RStudio, or into a Python environment, and create more sophisticated and rather more aesthetically pleasing plots. Okay, an easy way to export data generated in the model. Maybe I'll leave LibreOffice open for now. Okay, so this was version 2. I'm going to post this to the various course sites, and it is possible I will encounter some permissions issues while doing this if I haven't renewed the session. Yes, okay, so let me go log back in and engage in requisite frobbery, and I will then complete that posting. Okay, here we go. Models built in class. There we go. File. Okay. And we are added that in, and then to the fields course, I'm going to add in, oh no, okay, yeah, hey, sorry, I just want to make sure that everyone is able to follow this along. This, yeah. So I'm just going to call it ABM mobility V2, infection mobility, and here we go. Okay, and come and get it. Okay, so back to the fun minds. Okay, so we're going to kill this. Okay, let's start to work on something that further extends our abilities. We've already had some basic way of cross-sectional reporting, right? We could put in more statistics in evident ways that would report on count of people at home at any one time, count of people in a susceptible state at any one time. But we'll probably want to do something a little bit more interesting than this. One idea will be to report on the number of new cases of infection that have occurred over some period of time, say over the last day or over the last week. So I'm going to put in place a mechanism for that. These are what I referred to yesterday from this chair as flow statistics. So let's bend ourselves to that task. We're going to save this to version 3. Anticipating the work to come. And we're going to put into place mechanisms to do this said reporting of changes over time. Okay, so what we're going to do is as follows. We are going to add we're going to add requisite mechanisms to allow us to sample periodically a count that will be a tally that will be accumulating about how many people have gotten infected. We will have this running tally that will go for a day at a time. At the end of that day, we'll sample it. We will save that information away in a way that will allow it to be plotted, and we will zero that tally out. And the next day, we'll start to accumulate again. That stored version of it will be plotted in a live way as we're adding these things in. Okay, so let's bend ourselves to that task. So there's a couple of things that are needed. The first thing is we are going to add to the model a variable. We're going to add it to main. This is really important because we're going to be adding a cognate variable at an individual level later to person. So bear this in mind. This is going to be count cumulative infections. Okay. I could have called it count of cumulative infections. In a pinch, I would have called it cumulative infections. The type of this variable in main is int. It's a count. And it has an initial value of 0. It's going to return to that value every beginning of every day. Now, if we want to count the number of cumulative infections, where in the model would that have to be incremented? Like at what mechanism in the model would this variable need to be changed? Not use signals in an expressive hand gesture that it lies within the person, further down in the more detailed the model. This, folks, is where this mechanism characterizes an infection occurring in the model. Now, mind you, it could be that in some models, there'll be several places in the model, right? There might be some infections that occur from exposure to surfaces, some that occur, by extension from aerosols in the environment, and some from closer interactions. There could be HIV transmissions that occur because of needle sharing, and others that occur because of sexual contact. And we may, in general, we might wish to break those out or clump them. If you wish to just clump them, you could undergo what we're doing here for just a lumped one of these. Every time we increment the same variable. In other cases, we might have separate variables to indicate different particular pathways to infection. Here, our task is simpler. This is where infection occurs. This is the process by which a susceptible turns into infection. It's lent an appropriate name of infection and not, I would note, transition 47. Here, we need to here record that it was, that an infection has occurred. So in order to do that, we go to the action for this mechanism. We say main dot count cumulative infections, and we're going to increase this by 1. Now, putting an appropriate space between there, to signal clearly what we're dealing with, we could add in this sort of way. We could say this equals this plus 1. That is wordy, and it's wordy in a way that forces us to glance at this and see if it's the same as this. And there's actually an idiom, a programmer idiom, that there's actually 2 of them of relevance. We could say plus equals 1. And that says make it 1 bigger than it otherwise would have. There's even a terser idiom, which I will show, but from which I will retreat, chastened, that's plus plus. And you will see that sometimes. It is frequent enough, this idea of I want to increase it by 1, that it actually is lent its own operator. I find this an appropriate balance for those new to it. It tends to be transparent enough for those new to this that it doesn't throw them off, but terse enough it doesn't require extra cognitive overhead for those experienced to understand what's going on. By contrast, if we add this equals this whole thing plus 1, it does force us to kind of glance at both sides to make sure we understand what's going on, which imposes cognitive load where it needn't be imposed. Gratuitously imposes cognitive load. Take it from an old software engineer. Okay, so we do this equals this plus 1, and we should now have a variable that rises over time. Let's go watch our handiwork. Run early, run often, make sure it builds, make sure it's happy. Oh, I should have emphasized there needs to be a semicolon after it because we're telling do this, make this happen. This is a command. It's not just a formula that's computing something and giving back a value. We're actually changing something here. So this needs a semicolon after it, just like reporting out the status here with trace ln to the so-called console. Reporting what's going on needs a semicolon after it because it's doing something, that's undertaking some change, some command. So we need that. Okay, let's go run this thing. Run. Okay. And you'll notice that this is actually incrementing. It's rising over time, reflecting the cumulative number of infections. So even if we just had that, this might be instructive to examine. We could at any one time tell how many cumulative infections there have been, but we don't want to stop there. This is just the first part of a multi-stage episode. So we have our count of cumulative infections. Great. Now, we are going to go and put in place a plot that is going to report this. This is going to be familiar territory, but it's useful. There we go. And this is going to be cumulative infections plot. Great. Okay. This is going to be cumulative infections. Notice we're breaking it out into a different plot because the scale will be quite different than the current numbers that are infected. And this is going to be Maine, just going to be, since it's in Maine, we're in Maine, this thing lives in Maine, we're just going to say count cumulative infections. This is the value. Note I don't need a semicolon, it's just giving a value. So that's all we need to do. And we'll again have it report once a day. And we will engage in requisite frobbery of these things so that it's not brutally myopic time frame. So we could see a bit of a longer one. I apologize for this. Really, I should have made this 365 times 24 just to give it 365 days worth of hours. But I can't put an expression there. I actually have to go compute it, and I didn't have my heart. So I admire youthful vigor and exertion initiative. So 8,760 is the number. Young Matthews has schooled us. So there we go. And I will put it for this as well. And my conscience is salved, if I to speak in iambic pentameter. Okay. So here we go. And we will run this. And we can plot out as time goes on the number of the prevalent case count and the number of cumulative infections. The number of cumulative infections shoots up, and then it rises roughly linearly until said point where it might actually flatten out, meaning the infection is no longer spreading. And you can see we've had just short of 4,500 infections at that point. Okay, now we're at a waypoint in our exertions, but we've actually shown a useful mechanism in and of itself. And we're going to use this pattern to good effect. We're going to have a variant of it now. And I found that students, there's actually a way there's several ways we could take this, each with trade-offs. I found for some reason students tend to find it easier if I do it the following way. We're going to have a count cumulative infections for day. Count cumulative infections is over the entire time frame. Count cumulative infections for the day is going to be a running tally just for this day. What did I do? Well, I used a sleight of hand. I actually clicked on this, dragged, and dropped to copy it. I could alternatively have done a copy by keyboard action and paste just as well. And I renamed it for day. Okay, here we go. This too will live in Maine. Okay, next we're going to go to person. And with some hang from the trade-offs involved, the brutality of the repetition involved, I'm going to copy this line and say a for day here. So we're just going to have it increase on a per day basis. And I hope you'll forgive me that I haven't posted it. I'll be posting it after this thought is completed. Okay, so we're going to have a running tally per day. On a per day basis, we're going to be incrementing this count of cumulative infections, okay? On a per day basis. Okay, next. We are going to, so each time an infection occurs during the day, we're going to increment this. What's going to be different now is that this is going to be just a running tally for the day. So let's go to the palette. Let us go to this agent element palette. We're going to drag in an event, and this is going to be called new infections reporting event. Were we only health scientists, I would call this incidence reporting event or incident case count reporting event. I'm giving it a name. It's a little bit more intention revealing for those who are different background. New infections reporting event. This is going to be an event that goes off once per reporting period. So this is no longer going to occur once like our initial infection event. It's going to occur cyclically every day. So every day, at the end of the day, for us, a bell will toll. And this tolled bell is going to be reporting. It's going to be reporting the incident cases which have transpired in the past day. Okay? Okay. So here it goes. Every one day, this is going to happen. What is going to happen there? Well, two things are going to happen. One is we're going to take the tallied up to this very time, and we are going to squirrel it away where it can be appropriately graphed and exported later. Number two, we are going to zero it out so that we can begin the tally again tomorrow. Now, there's other ways we could have accomplished this. We could have taken the difference between the cumulative count now and as it was a day ago and taken those difference. For some reason, students have seemed to find that more confusing. But you should be aware if that's a rather pleasing option in my view. Here, though, we're going to store this away. And to do that, we're going to go back to the agent palette, to the analysis palette. And we're going to put into the model a data set. And I'm going to call this new infections data set. I'm just yearning to use the word incident case count data set, but I'm aware of, I speak to my audience. New infections data set. Okay. Now, we're going to keep up to, we can say how long it is. I'm going to say maximum 10,000. I could have made it longer than that. You certainly don't want it to be at the point where you start shedding samples. We will not update data automatically. We're going to add it into this explicitly. Okay. Okay. So, having created that data set, we should not log to the database. It's not on it anyway. Yeah. Okay, here we go. Now, the action here. When this event goes off, we will have new infections data set dot add count cumulative infections for day. So we're going to add this to the data set. So we're going to squirrel away the value we totaled up, our tally for the past day. It's going to have some number, 11 people infected in the last day. We're going to put it into this data set. Next, we're going to zero out that tally. Count cumulative infections per day, not count cumulative infections per day. We're going to set it to 0. We're going to reset it so that tomorrow will be a fresh day and we'll be accumulating counts there. Hmm? Now, this data set is going to be accumulating things. And, let's heed Jeff McDonald's exhortation of always keeping the model close to running. Let's heed my exhortation of build early, build often, and run early, run often. So we're going to go run this model, make sure it builds happily. I will be posting it forthwith. And here, you'll notice that as time goes on, we will have these samples accumulating as days go by. Here we go. We're several days in now. And indeed, in our data set, we are having a running count of the number of new infections in each successive day. And that's all nice and good. We can, in fact, take this, if we run it for considerable time, and this gets a large thing, we can take this, we can pause the model, we can take it, press this little copy button, and once again, we can go over and use a spreadsheet to its advantage, and we can export these number of new infections, 24 hours apart. These are the number of infections that have occurred at each day. Being clear, what's going on is that each time someone's infected, we are recording that in our tally. And then once a day, we're taking that total tally, we're adding it into this data set, and we're zeroing out that tally to start anew tomorrow. So it's recording a running count of those who were infected for the day, and then we export it. But let's create a little graph of it. We know all about graphs, and we know about 8760. So let's go drag this in here, and we will have, new infections time plot. Notice I like to give a name for a thing that communicates what it is. So when you see a list of names, you can immediately say, oh, that's this one, that's this one, that's this sort of thing, that sort of thing. I find that intention revealing. So this will say new infections. I'm tempted to say incident case counts. Okay, you'll forgive me. You could say new infections if you'd like, but potato, potato, tomato, tomato. Okay, for me, this is the intention revealing. And I'm going to say here the name of this data set. So now we're going to select data set. And which data set is it? Well, speak on. It is new infections data set, named worthy of itself. New infections data set. Okay. And we're going to update every day as we are wont. And we are going to keep 8760 samples as computed by Young Matthews. What's that? Sorry? Yes, you're right. Yes, this should be 365. Yes, you're right. Because it's 365 samples. The time window is 8760 time units. Yeah. Alternatively, we could have said 365 days. Yeah. Let's see what happens. Heck. I actually have not exercised that functionality in many a year if I've ever exercised it. Okay, here we go. Okay. That's maybe a comparatively newer software affordance. Okay, so here we have new infections data set. We're plotting out this data set that we created here. Okay. Time runs on. Let's build the model. It reports its happy camper status. Let's run the model. And let's see it run. Let's go up to our plots and let's view them. Okay, here we go. Here's our incident case counts over time. nicely displayed, characterizing the incident cases. This is the prevalent case counts. The incident case counts tend to be somewhat lower because people are recovering, and it generally takes more than 1 day to recover. Therefore, the number that are infected currently at any one time tends to be somewhat larger than the number that in the past day have gotten infected. Okay, so I'm going to post this for anyone who would like to grab onto it. I would welcome that. So this is going to be called Mobility Infection V3, and I'll post it. Do we need to post it locally? No. Okay. There we go. So for anyone who would like that, it is now posted. And I apologize for not making the name intentionally revealing, like saying, with incident case counts. Okay. So saved it to version 4. Time ticks on. We are now going to do something rather different for the crescendo, as it were, or for the grand finale. We are going to take our attention and we're going to actually display heterogeneity with analytics worthy of that and mechanisms worthy of it. Let us press ourselves to this task in the limited time that it is afforded us. Let's go to person. We are going to now record number of cumulative infections, but not across the entire population, but at an individual level, taking advantage of the individual lens afforded by agent-based model. Okay, to that end, we open person. We go to the palette, which speaks to us even now. We go to variable, and we place it in person. This is going to be count cumulative infections. And I'm tempted to say for person, just to keep it evident for everyone, to keep it in our mind, to avoid confusing. If I say count cumulative infections, you won't get confused. This is at an individual level. This is for that person. That's why it's a characteristic of that person, a property of that person. What sort of variable is it? It's not a double. Nay, it be an int. It starts like its aggregate cousin at an initial value of 0. Now, where, pray tell, is the value of this incremented? What changes the value of it? What mechanism? What pathway changes it?
The infection state transition.
Yeah, the infection transition once again. Now, this troubles me that we're just adding these things on here, and it relates to my comment yesterday that the code to actually undertake observation processes actually encroughs. It ends up like adding and sometimes obscuring core logic, or at least distracting you from attention to core logic. You could see there's a bunch of code here. And, if I had my druthers and I had 15 more minutes, I would carve out a function for this and encapsulate it. You notice I said this. I didn't just do this. I could have done this, but this is, it would have been just the same semantics, the same meaning. But by saying this, I'm emphasizing, look, I'm changing it for myself, okay? And it just brings our attention home when we look at this, that, wait, this is the one to change my own value.
In contrast to the mains above.
In contrast to the mains above, it kind of has a nice symmetry to it that brings home what's being incremented globally as an aspect of the whole model situation and what's being recorded for me. This refers to me. It's a reference to myself. It is optional here, but I would argue this is a case where it confers value by sharpening our thinking or by reminding us. Okay, So we're adding 1 to this thing. Okay, so let us run this model. We run it, and we go down to the individual level, and we see person. We could go here. We could see this person is yet untrammeled by illness. Now they've been infected once. Will they be infected again? Twice, 3, thrice, 11, etc. times. Okay. Okay. So we're recording this. Now let's display it. Let's display it in a worthy way. Well, okay. What am I going to not show you? Jeff McDonald long told me at my boot camps that the hard thing is deciding on the 90% not to give. So first of all, this is so easy, quick to do. In population, at an aggregate level, in population, in Maine, I'm going to go and I'm going to take, well, that's not what I'm going to take. I'm going to take name average infection count. Now, mind you, we can compute it by the cumulative divided by population size, since population size is fixed. But if we added varying population later, that wouldn't be so true. We're going to take the average of what expression? Remember, we call it agent. Agent dot, and it's cumulative. And let's see if today the gods of autocomplete favor us. They do not. So I think this is called cumulative infection count for person. Is that right? Well, let's build. Let's use building to our friend. No, it's cumulative infection count cumulative infections per person. When I was a young man and carried yet even then the blush of youth, I would have about 80 to 90% hit rate on my names. I could predict what exactly I'd name something, and I could reproduce that name from memory. But I'm addled by age, and my skills in that said area have been killed by too much autocomplete support. Count cumulative infections per person, is that it? Okay. Yes. Okay. For person. Yep. Okay. So this would take an average over everyone in the population. That's why condition is, if we want to only take it over males or females, or we only want to take it over those, who are juveniles, those below 18, we could do that with the condition. But I promised a crescendo, and I shall not disappoint. So, with your leave, I will turn to adding a pair of supports for said crescendo. So we go to the palette, we avail ourselves of the analysis part of the palette, and into this model, we will stick 2 things. Number 1, a histogram data object. This is going to be called count, cumulative infections per person histogram data. Okay, what it lacks in brevity, it makes up for in intention revealing clarity. Okay, it was troubling me to say cumulative infections histogram data because I don't want it to be confused with the aggregate one. I want it to be per person. And it is a histogram data object, and I want to convey it's a histogram. Okay, we won't change anything. We'll leave its bins to be 10. Maybe, yeah, fine. I'll leave its bins for 10 in the interest of time. Next, so that was a histogram data object from the top of the analysis palette. Next, in our closing minutes, I will complete the thought. We're going to add, and you will forgive me for my lapse. I thought that name wasn't the worst name I've ever created. So I'm going to copy that and I'm going to paste it here. But instead of histogram data, it'll be histogram. This will be the histogram. And this will be cumulative infections per person is the title. That again is just a piece of text. The histogram is the name of this histogram data object, which I copied. And I have secured an economy by having copied that name and used it not only for this, cutting off the histogram data component, just cutting off the data at the end, but I've also just put it here to refer to that. Make sure it builds. If you misspelt this, if I said .dat, it would complain and it would alert me to the fact that it doesn't know, it can't find that histogram data. You notice it says histogram confusing. It should be this histogram data object to which you refer to good effect. Okay? Okay, we're closing in on our court. We stand, dear listeners, on the cusp of greatness. Let us complete that thought. Let us secure the greatness of this session. Okay, so with that in mind, we will go down and we're going to do new infections reporting event. And you'll forgive me. No. Shall we do it? No. This is new infections. Let's put in a similar logic with the principle of separation of concerns. Let's put in an event. Let's call it cumulative infections per person reporting event. What it lacks of brevity, it makes up for it. Intention, revealing clarity. Okay. This too, well, at least we can rehearse time, exercise skills worth building. Okay, this is a timeout. It occurs cyclically, and we're going to say this occurs every week. We don't need it every day, every week. Every week, this will fire off. What shall it do? Well, this is getting to the crux of the matter. And now you will see the glory and the horror. Okay, so I'm going to put in place, I'm going to iterate across the population for, okay, now I've got to remember my Java syntax. No, for person P in population, indenting is a key skill. Indentation communicates. Indentation is a key part of rendering code clear and in a manner that communicates structure. It's easily ignored, but when we ignore it, we do so at our peril and the peril of all viewers. We also do so at the pains of acute aesthetic distress on the part of certain professors. Okay, so here, person, we are going to be populating this histogram data object. So here we're going to go. We created this histogram data object. It lived up here. Cumulative infection per person, histogram data. So first we have to clear it. Cumulative infections. Now this is where autocomplete is your friend. Go and choose the histogram data one. I'm moving it up and down, but it's this one here. Hey, oh, why aren't you doing that? Okay. I think it's called reset. Is my, yes. Okay. Okay. We reset it. We clear all values in there. We don't want to have previous values from previous reporting. Next, we go through and we go that same thing. We add into it, add the person's count cumulative times infections per person. That's for that person, the count of times they've been cumulatively infected. That was this variable that we added here that we increment. Remember, at an individual level, this one right here. So we are within this reporting event, adding that value in to our histogram data object. One by one, we go through each person in the population, adding each person's count of cumulative infections in to be summarized by the histogram. It needs a semicolon because we're doing something. We're commanding and we're saying, add this value to this histogram data. Exclamation. Well, it's like an exclamation. It's like an exhortation. And the way we signal that is by semicolons. Okay. You would think they might have denoted as exclamation points, but alas. Okay. So that's what we need to do. And let us turn ourselves, if we may, plot. Let us go and run this model. I'll build it early, build it often. And let's go plot out, oops, help if I ran it. Here we go. Initially, everyone has 0 infections per person. Then we start to get more infections, a greater variety. Some people have had up to 12 cumulative or up to 11. Some people have had the mode is somewhere between 4 and 6. Okay, now we could change declaratively. We could go to this histogram data object and we could have tweaked and set the number of bins that we want to say. We could set what those bins are, but I will leave it to the initiative of youth to engage in said process. We could also copy this. Notice we can engage in copying. Notice it gives the mean here. Unfortunately, it does not give the median, but it gives the mean, 10.83. I'm going to go over to my spreadsheet, and I'm going to paste this in, and what we will have is a characterization of the cumulative distribution function, the probability mass function associated with the number that have fallen between 4 and 6.4 infections, 6.4 and 8.8, 8.8. So this is giving the fraction of the population of people in the population who have had a count of infections cumulatively to this point that falls within that range. And I know these boundaries are not what you would prefer to impose, and I would invite you to go and, change the value, the interval size to be fixed at 1 or 2, and to tailor those to your content. But we do have a probability mass function and a cumulative distribution function, which we've imposed. But we are hopefully somewhat inspired by the crescendo of sorts. We have reached the summit of our exertions today, and we have exhausted the allotment of time that we have for today, and I've kept you beyond the promised time. My regrets at that. I hope this is useful. I will go post this model immediately for anyone who got lost following along, and I look forward to seeing everyone from this seat tomorrow. Take care there.